restart this session and minimize my GoToMeeting screen. Find the missing sides, leave answer in radical format. You don't have to show your work?
No.
So you said the cosine of 60 degrees was equal to this side over 10, and that side was 5 because the cosine of 60 degrees is 1/2. All right, without your work being on here, it's difficult for me to see anything. You did this using trig functions?
Yeah.
Okay. Well, so far your answers look correct. That would be root 2 and 2, so 21 times both. That's sine of 30 degrees is 1/2, so this side's got to be half of that side. It is. Okay, how about let's do 5, and let me write it on there. So give me the trig function. I'm going to make you show your work. So on number 5, tell me, we'll call this y, and we'll call this x. Okay?
Okay.
Now give me an equation to solve for either one.
Y equals 2 times 9.
You know, there's a secret to trig. Let me tell you what it is. When you begin all of your equations, start with the trig function. So figure out in advance what trig function you want to use to solve for, let's say, y. What is it going to be?
I don't know. I wasn't really sure about 5 and 6 because
okay, well, here's what you're looking for. You're looking, if we're solving for, let's talk about y, first of all. Well, you don't want to relate y to x. In other words, you don't want to say the sine of 30 degrees equals y over x, because that's two variables. You can't solve for that. So you've got to relate y to the number 9. Well, what trig function relates y and 9, those two sides?
One has root 3, one doesn't.
Hold on, no. Here's what I'm talking about. Which one of these relates those two sides? Y is the opposite. 9 is the adjacent. That's the one. So, when you write your equation that you're going to solve, start with the trig function. I know it's tangent. What's the rest of it?
Y over 9.
Tangent of 30 degrees, when I say the rest of it, I mean everything, equals y over 9, yeah. So, y is equal to 9 times tangent of 30 degrees. And always remember, these are just numbers that you're going to get out of your calculator, or you know that the tangent of 30 degrees we know to be 1 over root 3. Okay, so it ends up being 9 over root 3, and go ahead and rationalize that if you need to. And let's talk about that. How much have we talked about rationalizing? That's our answer. Okay. Well, 9 over root 3. Is your teacher going to let you turn that in as an answer?
I think so.
Oh, good. I hope so. I hope so, actually. That is the new trend in trig teaching, is to let students leave it in unrationalized form. And it's because so many trig functions are reciprocals of the other. In other words, if the tangent, if y, the side y is equal to 9 over root 3, if we rationalize that, it actually does simplify a little bit. In other words, I end up with 9 root 3 in the top, I end up with 3 in the bottom, that goes away, that goes away, so we end up with 3 root 3. I have to admit that's an awful lot prettier than 9 divided by root 3.
Yeah.
But it's more of a philosophical question. It really is. Trig is a whole lot easier if you don't have to worry about rationalizing stuff. It just is. If you can let students leave answers in non-rationalized form, they're going to do better. It's annoying to have to rationalize these things, and not only that, a lot of times when you rationalize something, then the reciprocal needs rationalizing, and you end up creating a lot more work for yourself. Okay? Now, over here on 6, I'm going to call that y, and I'm going to call that z. The hypotenuse. Hold on a second. Jesus. Can't draw z even. What equation is going to let me solve for y? What trig function, I mean? Not. First, let's figure out the trig function.
Tangent.
Good. So I'm going to start my equation off with tangent. Fill in everything else. Tangent of what?
Of 30.
Equals
y over 12.
Which makes y equal 12 tangent of 30. Again, that's 12 over root 3. So if they let you give that answer, give that answer. If it has to be rationalized, again, this is going to look a lot nicer rationalized. It's going to be 4 root 3. So it really kind of depends on your teacher. What they've taught for 8 years since I've been a tutor is you rationalize everything. That's just the way you do it. And it was just this year that I had one student that told me his teacher told him not to rationalize stuff in trig. And that was the smartest thing I had heard anybody say in a long time. Rationalizing stuff in trig is not worth the time or the efforts. All right. So we've done 5 and 6. What's this angle right there, theta?
At 22.
Okay. That's what's called the reference angle. In other words, the reference angle is always the angle that the ray makes with the x-axis. Okay, it's that simple. Now, so far in the trig that we have worked on, I've always said make any angle that you find that's not in the first quadrant, in other words, if it's in the second, third, or fourth quadrant, turn it into an equivalent first quadrant angle. That's the same as the reference angle. There's no mystery, and there's no, in other words, we could always be figuring out the reference angle. And that happens to be the same trig function as that 22-degree angle. So that's why I tell all my students, figure out what the equivalent first quadrant angle is. It's what the school system teaches is the reference angle. Okay, this one you went around 180 clockwise, and then you must have gone another 65. Now what's this? Oh, then identify the reference angle. Yeah, okay, so that's 65. It's always the angle made with the x-axis. Okay, here you went around counterclockwise once entirely, and then again another 145 degrees, and that is the reference angle, and it is 35 degrees. Okay. So the next one, you converted to degrees just to make it, nothing wrong with doing that at all. So what'd you get? You got the pi's cancel. The 9 turns into 20, and I got 20 times 16. That's 320 degrees in a counterclockwise manner, which leaves that angle as 40. Now notice that all of these agree with my definitions that I taught you. In other words, if you use 360 minus theta, you get the reference angle. In the third quadrant, if you use theta minus 180, you get the reference angle. In the second quadrant, if you use 180 minus theta, you get the reference angle. So those three formulas are meant to give you the reference angle, or what I call the equivalent first quadrant angle. Okay, so over here we got what? 140 degrees. Looks like it should be negative. Am I mistaken? See that negative sign right there?
Oh.
Okay, so all you did was go the wrong way. That's okay. So that's what your ray should have looked like. Turns out the reference angle is going to be the same, whether you went the right way or the wrong way. That angle is one of the few times in math you can make an error and still get the right answer. In other words, that's either minus 140 degrees, which is what it's supposed to be, but even if you use 140 degrees, you get the same reference angle. Reference angle is the angle made with the x-axis. So that theta is the same as that theta, and they're both 40 degrees. However, you might have lost a point on this one. Just didn't draw it going clockwise instead of counterclockwise. Okay. This one looks pretty good. This 12 goes into that 180 15 times. Good thing to remember. 11 times 15 is 165, making the reference angle 15 degrees. Okay. Is that everything on this? Oh, no, we got more. Include your work. And here we're converting from degrees to radians. Okay. That's good. How'd you figure out that 235 divided by 180 was 47 over 36? Must be both divisible by 5. Okay. That's good. Now, notice that they're doing it in the normal way when they're converting from radians to degrees, right? In other words, they're using their conversion factor. And you write that out, and then you use a calculator to figure out what that is. Notice my way is a little easier, I think. You can use it whatever way you want, but first of all, hold on a second. I gotta take a picture. And I don't want to confuse you any, but pi over 15 is what? Remember that number and that number have to multiply to 180. It means that's got to be 12. So pi over 15 is 12 degrees. Therefore, 7 pi over 15 is 7 times 12, 84 degrees. Now, I don't know, okay, I don't suppose it matters which method you use. Use whichever one works for you. And this is a fine one. That one's correct. Coordinates of the point P on the unit circle. Wow, really? Okay. You have to tell me how you did these. They want to know what the coordinates of that point right there are. Give me some equations that are going to let us come up with this answer. First of all, what's the reference angle? Let's put a reference angle in there because it's going to be easier to analyze if I have a reference angle.
20 degrees.
Okay. What's the hypotenuse length? Of that triangle we've drawn?
1.
Yeah, that's the key. In other words, we had to have more information, otherwise I couldn't solve for anything. But now we can solve for everything there. So what is the, first of all, what's the x and y coordinate of that point? Is it not cosine of theta comma sine of theta?
Yeah.
Okay, so let's figure out what the cosine of 20 degrees is. According to my triangle, what is it? If that's x and that's y.
0.93.
Well, okay, so that's the value? Yeah, well, here's what I'm trying to get, is the cosine of 20 degrees equals the x coordinate that we're asked about divided by 1, the hypotenuse, which means the cosine of 20 degrees is the x coordinate. And it always is. When you're talking about the unit circle, the x and y coordinates are always the cosine of that angle and the sine of that angle. Now, should we take the cosine of 20 degrees or should we take the cosine of 200 if we have to use a calculator?
200.
You're right. No need to use that 20-degree angle here. If we're using a calculator, if it was 210, then we wouldn't need a calculator and I might choose to work with the reference angle. But, and your calculator tells you that that is a minus 0.94 rounded up. Correct? That's where you got that number?
Yeah.
Okay, and then tell me what the y coordinate is, and tell me what it is that I should write. In other words, you really probably should give a little bit more work here. Just giving the answers doesn't tell the teacher you know much. But if you were to write as little as this much, what I've written right here, she knows you're taking the cosine of 200 degrees to get the x coordinate. And then how am I going to get the y coordinate?
Sine of 200.
And that's equal to minus 3.4. Notice the signs are appropriate and proper. Both cosine and sine are negative in the third quadrant. And you can see why. In other words, this x measurement right there is in the negative direction. this y measurement right there is in the negative direction. And that's why cosine is negative in the third quadrant, and so is sine. Incidentally, the hypotenuse is always positive. And if that seems strange, it's because this is really your first exposure to polar coordinates. The unit circle is polar coordinates. They don't tell you that when they introduce you to it, but it is. And in polar coordinates, r is always a positive number, no matter which direction it goes. So that's why the hypotenuse is always a positive 1. Now, let's look at this one here. So tell me how you did this one. How'd you get the 0.91? Tell me the equation you put into your calculator.
Just cosine of 335.
Okay, and how about this one?
Sine of 335.
Okay, over here on number 19. Notice that we have a negative angle, but it puts it in the third quadrant. So we know our sine or our cosine and sine need to both be negative, and they are. So what'd you enter into your calculator here? You entered the cosine of minus 123?
No.
Did you figure out the positive angle and enter the cosine of that?
Yeah.
You could have done either. Do you have your calculator in front of you?
Yeah.
Most direct way to do it is type cosine of minus 123. See if it gives you that same negative.
Negative 0.544.
Okay, good. Saves you a step, right? Because the way you did it, you had to subtract that from 360. Well, you don't need to do that. All right, let me close this out. We're done with this page, correct? Yeah. Next one's the middle or the far left?
I think it's the left.
Okay. I don't know if it even matters whether we have to go in order here or not, but in case we run out of time, do we pick the right one?
Yeah.
Okay. Perfect. What's that answer? Negative 2?
Yeah.
Okay. Here, let me just get ready to write in case I need to. Yeah, I don't know if your teacher taught you to do this, but you're doing kind of what I recommend everybody does. When they ask you to evaluate a log, I make up a variable and I put it in, x. Then, all I have to do is rewrite that as an exponential expression, which you've done perfectly, and now you can solve it. Now it's pretty easy to solve. Same thing in B. 8 to the x power equals 4. Interesting.
You got something on there. I didn't know if you want me to try. I have a little mint to get that out of there.
2 cubed, so 2 to the 3x equals 2. What's that? 2 squared, okay. So now you can say 3x equals 2, x equals 2/3, perfect. This one over here, there's an e right there, so, and an x right there, so I get e to the x equals e to the 1/2, so x equals 1/2, very good. This one is 64 to the x power equals 1/4, and then I find a common exponential base, which is what you're doing in all of these. You might do this slightly different in terms of the work. In other words, I would say that's 4 to the 3rd. That's the number 64, and I'm taking it to the x power, And then that turns into 4 to the 3x when you apply the rules of exponents. It's not terribly clear the way you've done it, how you got from this step to that step. In other words, you kind of left out a step. May or may not be important. I don't know how much your teacher looks at your work. All right, let's look at 31, condensing these things. How do I know you know how to do this?
Well, I'm not sure.
Actually, you got it wrong. What is this thing right here? Is that a plus sign?
Yeah.
Okay. Well, here's what we have. Those two log statements are being added. What that means is that if I condense it into a single log statement, those arguments have to be multiplied. Okay? And the first step of taking this 3 and putting it there, that's a good one. You can always do that. And then take that 1/3 and put it there. You can always do that. And now you have the log of x cubed times 27 to the 1/3. Well, what's 27 to the 1/3? It's the cube root. Cube root of 27.
3.
So that becomes 3x cubed in the numerator. So, and they always want you to simplify these as much as you can. So there's my numerator. And my denominator, you can leave it the way you did it. There's no need to expand that. Whenever you're dealing with a power greater than 2, you know that they don't expect you to expand it. You'd be still working on this problem if you had to expand that. That's why you know they don't want you to do it. Okay? All right, but make sure you take addition and make it multiplication, and you take subtraction and make it division. Let's take a look at this other one.
Okay.
Again, you've added. That needs,
yeah, I just noticed that.
That needs to be a multiplication. Other than that, looks pretty good. Is that what exponent? That's a 3, okay. Yeah, it looks like you know what you're doing on these. And you're only making one mistake, and that is you're adding a new argument. And always remember one thing about logs, is you never do the same thing. In other words, if the logs are being added, you're never going to add the two arguments. That's not happening. You do not get the log of A plus B. That's not equal to the log of A plus the log of B. That never is the case. It's only the case if it's A times B and the argument turns into addition. But the thing to remember is this is never the same as that. They're always different. If this is division, this is subtraction. If this is multiplication, this is addition. That's one way to remember it, is you're always changing it.
Hey, what's awesome,
Now we're expanding. Let me have a look at this.
Hey, all the lights are on.
Where'd this 1/2 come from?
Log base 4 of 2.
Why is it at the very beginning? Did you add it afterwards?
Well, I had it first as 5 log base 4, but 2x to the fifth. But then I went to her key, and then she put it in front as a 1/2, so I had to change it.
Okay. If these answers are coming from the key, then you're doing yourself a disservice, Nicholas. I don't need those answers.
No,
Okay.
oh no, I actually did them, but
Okay.
I went to the key
Okay.
after and checked, and that's what I got them.
That's fine. That's fine. But in other words, it's a more difficult tutoring session if we're looking at the answer. It just is.
It's just my mom wanted me to do the problems.
I would rather not have the keys on there when we're doing these, because otherwise I have no real way of telling if you really know how to do it or not. Because I can't tell if this is your work or if that's her work. It's not a big thing, but let's go through exactly how we would do this. Okay, let's not put that at the beginning, because that's not the way we're going to do this thing. We've got a couple of things going on there. We got multiplication going on there between those, and then this is being divided. So we need at a minimum 3 log statements to expand this. What's the first one? They're all log base 4. Okay, so here's what she did. Okay, so she made that her first statement, right?
Yeah.
Because 2 is multiplying x to the 5th. So then she added log base 4 of x to the 5th, which becomes the 5 in front, like that. And then more addition, because they're all multiplying y to the 1/2, which becomes 1/2 log of y, all of them base 4. And then finally, to handle that x minus 1 that's being divided, we need to subtract the log base 4 of x minus 1. Now, the only one of these expressions that we can do more with is this one. And you're right. 4 to what number equals 2? That's 1/2. So I'm going to write it exactly the way she's written it in her key. But that's the way you want to do it. Now, I actually had some, oh no I didn't. No, I'm sorry. There were definitely 4 log statements. I cannot do anything with that 2 other than what I did. Notice that it's tempting to try to take that 2 and multiply it by 5 and make it x to the 10th, right? Aren't we supposed to be able to do that? No. The 2 would have to be in front of the log to be able to do that. If the 2 is part of the argument being this part here, then you cannot use the rules of logs and make that 2 part of that exponent. Doesn't work like that. So you have to make the 2 a multiplier, which means you have to have the log base 4 of 2 plus that part, plus that part, minus that part. All right. Check for extraneous solutions. Are you looking at this document in front of you?
Mm-hmm.
Okay. Let's start it from scratch. What's the first thing I'm going to do here? In other words, here, let's do away with that. We don't want to be seeing that. Seriously, it's hurting you, not helping you. So what I'm going to do, I'm going to subtract 7 from both sides. Okay, now what?
Get the log we're in, yeah.
Now, when you've got a log equation that you don't know how to solve, almost always you have to convert it to an exponential expression. Well, what's the exponential expression here?
X plus 4 to the third.
What's that? Start with the base. What's the base here? It's e, right?
Yeah.
So it's e to the third equals the argument. The way I remember it is always it's the number on the far left raised to the power on the far right equals the number in the middle. At least that works as long as the natural log is on the left side. If the natural log's on the right side, then you can't use that rule. But in this case, you can use it. And notice what happens. This is a number. You can get that number out of your calculator. So my answer is e cubed minus 4. That's how I get whatever number she put down there. Got it?
Yeah.
Understand? Okay. Let's do this one. Over here, I got 120 equals 3 to the 2x. What's my first step?
Divide by 3.
Hold on, my pen just gave out. Just a second. Yeah. Let me think. This happened earlier today, and I had to unplug. Oh, that's not pretty. You never want to see that. Let me close this out. Try reopening it. See if that solves the problem. Does not. I'm probably going to have to unplug my drawing tablet and plug it back in. Hold on one second. Nicholas, apologize. I had to do this earlier today too. What's causing that, do you suppose? You're not a super whiz at computers? Alright. So you're right. First step is to divide both sides by 3. In other words, once we get it so that the e to the 2x is isolated, then we can take the logs of both sides, or the natural log of both sides, which is what she's done. Take the natural log of both sides, you get natural log of 40 equals 2x times the natural log of e, but the natural log of e is always 1. So that's why she didn't write it. And then x is natural log of 40 divided by 2. I'm assuming that's the correct answer. Okay. Now, some exponential equations, not very many, but some, can be solved without using logs. And this is one of them, because there's a common exponential base. What's the common exponential base between 1/4 and 32? Okay. And it's 1/4 can be expressed as 2 to the minus 2. 32 can be expressed as 2 to the 5th. And then you multiply exponents using the rules for exponents. And then you equate the exponents. In other words, the next step is if I've got 2 to one exponent equals 2 to another exponent, then I got the exponents have to be the same. And looks like you did the math correctly. Okay, that looks good. Over here, let's solve 36. Good. There are no answers on it. So what's the next thing I'm going to do? How do you solve log equations? That's the real question. And the answer is you condense wherever possible. Okay, I got two log expressions right there. Let's turn them into one. We have rules for doing that. What's the single log expression that represents the left side?
3x plus 7 times 6.
Correct. Which is 18x plus 42. In other words, that's what that becomes. It's the log of 3x plus 7 times 6, but the 6 has to multiply both terms. And then if you get that's equal to that log, what can you do now? In other words, if I get the log of one expression equals the same log base of another expression, what can I do with the two arguments?
Divide them.
Make them equal. Not divide them. Make them equal. Like I said, if I've got the log of one thing, 18x plus 42, equals the log of another thing, 4x plus 2, then my one thing has to be equal to my other thing. So it's 18x plus 42 equals 4x plus 2. One way to think about it is you're dividing both sides by log, even though that's not a great way to think about it because that's not really what you're doing. The log is not a multiplier here. That's strictly terminology. It's the log of that expression. And then if you solve that, you get 14x equals minus 40, x equals minus 20 over 7. All right, number 37. What in the world are they giving you this problem for? This is pre-calc, first of all. Most students do not learn how to do this problem until they get to pre-calc. Now, first of all, let me ask some things. Are you allowed to use your calculator on this?
I don't know.
What kind of calculator do you have?
I'm using my phone right now, but I have a 84.
Well, let's make sure you know how to do this problem on your calculator. Your phone's not going to do it, I don't believe. Your phone's not a graphing calculator, is it? Or is it? Maybe it is.
No.
You can use Wolfram Alpha. Do you know how to go to Wolfram Alpha? Not only will Wolfram Alpha give you the zeros easier than your TI-84 will, because your TI-84, you have to graph that, request the zeros, put it on trace, you got to do all kinds of things. But if you put that into Wolfram Alpha, it will tell you your 3 zeros automatically. So Wolfram Alpha is actually a lot more powerful than any of your calculators that you might be using. Now, I don't know that they necessarily want you to use a calculator on this, but the other alternative is about a 20-minute solution. So I gotta think they want you to use your calculator, but I'm not positive. You want to put it into Wolfram Alpha, or you want me to?
You can.
Okay, I'll do it. I'm going to open it up, and is all I have to do is find Wolfram Alpha on here. How come I don't see it? Here it is. have to enter it as a y equals or anything. Is all I have to do is enter it as I see it. In other words, x cubed plus 9x squared plus 27x plus 35. I don't have to enter the y. I just have to get it in there. And if I want to know whether I got it in there correctly or not, it's going to show me what I typed in. I typed it in perfect. You can see from the graph how many real zeros are there. Looking at that.
1.
How many?
1.
Okay, which means there's how many imaginary zeros?
3.
2. There could be at most 3 zeros to a cubic, or 4 zeros to a quartic, or 2 zeros to a quadratic. The number of possible zeros always matches the degree of the polynomial. Now, notice that if I scroll down, it gives me the only real root, which is minus 5, and then it gives me the 2 imaginary roots. Minus 2 minus root 3i and minus 2 plus root 3i. And in case you didn't know, the imaginary roots always come in pairs. One is merely the conjugate of the other. You never have one imaginary root. Always in pair. Now, let's talk about what they might have wanted you to do here. Can't talk about it without talking about P over Q. Does that ring any bells?
No.
No? They haven't given you the rational factor theorem yet? Here's what the rational factor theorem says. I'm going to ask because if you had to do this manually, you would have to use the rational factor theorem. And what the rational factor theorem says is if there is a rational zero of this polynomial, then its numerator has to be a factor of that constant, and its denominator has to be a factor of that coefficient. So the two most important numbers are the constant and the coefficient of the x cubed term. So here are my possible answers. Plus or minus 7, plus or minus 5, plus or minus 35, plus or minus 1. In other words, what the rational factor theorem says is that if I have a rational zero, it's got to be one of these 8 numbers. That's it. And when we used the computer to get it, we found out that that was it right there. X minus 5 was one, or the zero, one of the zeros, the rational zero, was minus 5. Now, how would I get that? If you had synthetic division?
Yeah.
Okay. Well, they may have intended you to solve this without a calculator. And what I'm going to do is I'm going to take this cubic and I'm going to start dividing it synthetically by all of these possible 8 solutions, starting with the 1, because the 1 is the easiest one. I would try plus 1. That didn't work. I would try minus 1. If that didn't work, I would try plus 5. If that didn't work, I'd try minus 5, and that works. And by working, I mean that when you divide this polynomial by one of these zeros, if you get a 0 remainder, then that is a factor. You have found the solution. The whole key is that when you divide your polynomial by your potential 0, you must get a 0 remainder. If you get a remainder of 1 or 2 or 3, then you have not found the 0. And so it becomes a trial and error process. And I mean trial and error. I would have had no clue that -5 was the 0 without Wolfram alpha. But I can certainly test each of these 8 numbers. Incidentally, when you use this rational factor theorem, it's always plus or minus with every single one. In other words, all of the factors of 35 end up being plus or minus. And I do have a denominator, but the denominator is plus or minus 1. So I didn't put it in there. It's not always 1, though. Okay? So, like I said, without knowing what the 0 is, I would just randomly start synthetically dividing by these. In other words, just so you see what I'm talking about, let me take what we know to be the 0, and let's synthetically divide it into that. Now, Wolfram alpha told us that -5 was a 0. What that means is that has to be 0 right there. Okay, well, if I synthetically divide it, what's the first step for synthetic division here?
Drop the 1.
Okay, and then next?
1 times the -5.
Okay. If you know that, I'll finish it out. Just wanted to make sure you knew the first steps. And indeed, I get a 0 remainder. And now I know that -5 is one of the factors. What's the other factor? Now that I know one of them, what's left? In other words, I know that x plus 5 is one of the factors, right? If the 0 is -5, then one of the factors has to be x plus 5. How do I know what the other factor is?
By using the quadratic formula, because...
Well, not really. I mean, just see what I got down here? That's the equivalent of x squared plus 4x plus 7. So that's what I have left. In other words, when I divide this cubic by a linear factor, I'm left with a quadratic. And now you're right. I can use the quadratic formula to solve this for my imaginary solutions. Although they don't always make you do that. A lot of times when they say factor down a cubic, they want you to take it down to its linear factors and its irreducible quadratics. And that's what that thing is an irreducible quadratic. Irreducible because it only has complex solutions. It does not have real solutions. If it had real solutions, they would want you to find them. And then you would list the 3 linear factors. But most of the time when you've got imaginary solutions of your remaining quadratic, you leave it as a quadratic. So I would give that as my 3 factors. Although this specifically says find all of the zeros, which means they want you to use the quadratic on this. And if I did, I would find my zeros. We won't do it because we looked at Wolfram alpha and we already know what they are. Alright, let's see if there's one last thing we can do in 4 minutes. So we're done with this page. That was the left, right? Correct?
Yeah.
So we've got the middle page only. What kind of phone are you using to take these pictures?
An LG.
Ah, it's not an iPhone. I knew that. iPhones have better cameras. Or else, yeah, and an iPhone either comes in really, really blurry or really crystal clear, depending on whether people send it as a small or a large image. Whereas this is neither. It's readable, but it certainly isn't crystal clear, and it's not so blurry that I can't read it. That tells me you didn't do it with an iPhone.
Yeah, I was just...
Which is fine. Don't get me wrong. I don't have an iPhone either. I use a Samsung. But interesting how one can tell. All right, 20. I'll do this real quick. When they give you one trig function and what quadrant it's in, the problem really becomes rather easy. The solution is always draw a triangle. Even though this may not be the way they teach you to do this in class, this is the best way to do it, trust me. Draw a triangle and label theta. Now, dimension that triangle as much as you can. Tell me what its sides are that you know at the moment. Bottom side is what?
15 or 9
Hypotenuse
is 15.
Okay. That makes this the square root of 225 minus 81. Square root of 225 minus 81, which is the square root of 144, which is 12. Okay, in other words, as long as they give you two sides of that triangle, you can always use the Pythagorean theorem to calculate the third side, no matter what it is. Now I have everything dimensioned. I can figure out what sine of theta is. What's sine of theta? Read my triangle.
It's a 9 over 12. Or
It's 12 over
15.
15. In other words, it's opposite over hypotenuse. Now we got to put a plus or minus sign. This is the way I do all trig functions. I figure out the number first, and then I figure out whether it's plus or minus. Well, what quadrant are we in?
The fourth.
What sign in the fourth?
The negative.
That's how I do it. And then, of course, that can be simplified, and you do want to simplify it to 4/5. You never want to give an answer that's not simplified if you can simplify it. Okay? So that's the way, in other words, I could have figured out all 6 trig functions. As long as they gave me one of them. As long as they tell me which one, that lets me do two sides of that triangle. I can always calculate the third side. They tell me the quadrant, so I'll know what its plus or minus sign is on any trig function you want to ask about. Had they said, what's the tangent of theta? Tangent of theta is 12 over 9. If they'd have said, what's the cotangent of theta? 9 over 12. And then you put the appropriate plus or minus sign on, but that's a good method and process to use. Always put that on at the end. All right, Nicholas, it's 8:30. I'm going to let you go.
Okay.
And have a good rest of your weekend. And I will talk to you, or rest of your Easter even. I will talk to you next time.
Okay.
All right.
Bye.
Bye-bye.